Hello everyone, and welcome to this video on using the product property to multiply radical expressions. Alright, so in this video I'm going to start off by introducing this product property for multiplying radicals or multiplying roots, and then we'll have several examples using that property. Okay, so what is this product property for radicals? Right. So this is a statement saying the following. If I have a radical, right, you see the radical symbol, right, the root symbol, and then index n, okay? If I take the nth root of some radicand, right, some number underneath the radical a, right, capital A there, and I multiply this by, right, little dot for multiplication, and I multiply by the same radical symbol, all right, so another nth root. Right, so notice how both these radicals have the same index. And I multiply by the nth root of b. That is going to be equal to the nth root of the product of where the new radicand is just the product of the old radicand. So inside the radical here I have a times b, or just ab. All right. Now this is of course only as long as the nth root of a and the nth root of b, again, and the nth root of b, both of them are real numbers, we can use this property. Okay, that's key. So all this means is, if n is an even integer, right, so if I'm doing a product of square roots, a and b have to be non-negative, remember, or fourth roots, right? Whenever we're taking even roots, the radicand has to be non-negative for it to be a real number, right? If the radicand was negative, we'd have what's called an imaginary or a non-real number. Again, we'll get into imaginaries and numbers that are not real numbers in a later video. All right. Okay, so this is huge right here. Keep this in mind. All right, the product of two of the same radical, two nth roots. So again, as long as the nth root of a and nth root of b are real numbers. So for example, if I took the square root of 5 and multiplied it by the square root of say 7, these are both real, right? You have an even root, right? Square root, and the radicands are both non-negative, right? 5 is the radicand of this radical, 7 of that radical. So these are both real numbers, right? The square root of 5 and the square root of 7. So in this case, we can use the property if we want to. Alright, so then the square root of 5, and I'll have other examples later too, times the square root of 7. You can use the property and say this is equal to the square root, notice again the same radical throughout, of 5 times 7 as the new radicand, or just the square root of 35. Right, and if you want to punch these in a calculator and see, just do that real quick off to the side here. If I do the square root of 5, right, times the square root of 7, that number is equivalent to 5.916079, the crazy decimal. And then take a look at the square root of 35, right, the other side, and you'll see it is indeed the same number. Okay, 5.916 something. All right. Now if you have a case where one of these is not real, you can't use the property. Right? So another example here would be if I had, if I said, what's the fourth root? The fourth root of 8 multiplied by the fourth root of, say, negative 7. This first number, the fourth root of 8, it's an even root with a non-negative radicand. 8's not negative. So this is a real number, right? The fourth root of 8. That's real. But this number here, right, the fourth root, an even root of a negative radicand, is not a real number. All right, and that's important, because if you see that, then for this particular example, we cannot use this property in the box up here, the product property. All right, so just be very, so I can't say that this is the fourth root of 8 times negative 7. It's not the fourth root of negative 56. We cannot use this property. This property is only for real numbers. I can't emphasize that enough. And really the only time you're going to have to pay attention to that is when the index is even, right? When you're taking an even root, because when the index is odd, if you're taking cube roots or fifth roots or whatever, 5, 3, 5, 7, 9, etc. It doesn't matter what the radicand is. The odd root of a positive number is real, the odd root of a negative number is real, and the odd root of 0 is 0, which is real. Right? So you can take the odd roots of anything. It's really only when you have an even index like 4 or 2 or 6 or whatever that you have to really pay attention to whether or not you can use this property. Right? So be careful. All right. So that's all I have. That's for the property. Now I'm just going to go over several examples where we first have to ask ourselves, is this property able to be even used? Are these numbers real or not? And then we go about using them. All right. So my first example is something similar to this square root of 5 times square root of 7. I have, and the instructions for all my examples in the rest of the video are the following. Multiply each radical expression. Okay, so here I have the square root of 11 times the square root of 7. So both the same radical, right, just like in the property. The question is, are these both real numbers? And they are, right? Again, these are even roots, square roots, and look at the radicands. 11 and 7, those are both non-negative radicands. Those are both non-negative numbers. So these are both real, all right, which is great. And since they're both real numbers, I can employ this property. I can use it. Employ. Yeah. So this will be equivalent to, right, the square root of 11 times the square root of 7 will be equal to the square root, and then the new again, square roots throughout, and the new radicand is going to be 11 times 7, or just the square root of 77. All right, and there we go. All right. And again, if you want to check, right, now the square root of 77 isn't a really nice number. Right? I don't know a number that when you square it, a non-negative number that when you square it gives me 77. I know that 8 squared is 64. And 9 squared is 81. So this is going to be between 8 and 9, right? And let's see that. Again, I'll pop the calculator up here. So what is the square root of 77, right? It's 8.7749, blah, 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 right? And let's check, is this indeed equal to the square root of 11 times the square root of 7? And it should be if this property is truly a true statement. And look at that, it is, right? 8.7749, so on. Right? They're the same number. Great. But you got to keep that in mind, though. Are these two real? All right. And the same thing would go this way as well. If you decide to take the nth root of a product and split it up, you can only split it up into a product of real numbers. Right? So you be careful with that as well. All right, my next example. Got the fourth root of 6 times the fourth root of 7. So again, I have a product of two even roots, fourth roots. So the radicands, in order for the numbers to be real numbers, the radicands need to be non-negative, and they are again. 6 is non-negative, 7 is not negative. So again, in this example, both numbers are real. The fourth root of 6 is a real number. The fourth root of 7 is a real number. So I can use the property. Since these are both real, I can now state that this product is equivalent to the fourth root. Again, notice fourth roots throughout, right? The same index on the radicals throughout, of, and then the new radicand is the product of the other two, right? 6 times 7. So we're getting here the fourth root of 6 times 7, 42. And that's it. Right? And we'll talk about how to know when a radical is simplified in a future video very, very soon. But I'm just gonna leave it like this for now. And this is simplified. I'm not gonna say it isn't. We'll do that later in a later video. And then what is this? This is again not a nice number, because 42 is not a nice perfect fourth power. 2 to the fourth is 16. 3 to the fourth is 81, and 42 is between 16 and 81. So the fourth root of 42 is going to be between 2 and 3, right? Between the fourth root of 16 and the fourth root of 81. Again, the non-negative, right? Whenever you see this symbol with an even index, it's asking for the non-negative root. So let's check it. So I'm going to go fourth root here. There's a way to enter roots on this. I have TI-84 here. Just hit the math button, go down to this root with the x there, enter the fourth, enter the index of 4. Got a fourth root of 6 times the fourth root of 7, and we're getting this 2 point, so like I said, it was going to be between 2 and 3. 2.545729895, right? It keeps going on forever with most likely irrational, without ending, without having a repeating pattern. And let's see if that's indeed equal to the fourth root of 42. So fourth root of 42, and yes it is, 2.547299895, and so on. Great. All right. Now my next examples, my last two examples, have variables involved. All right, so the first two are just a bunch of numbers, right? Square root of 11, square root of 7, fourth root of 6, fourth root of 7. My last two examples have variables involved, so you really have to pay attention. You really have to focus on, when are these roots, when are these radicals going to be real numbers, right? Remember, I said we can only use this property if the two radicals represent, if they are real numbers. So here I have the square root of x minus 5 and, times the square root of x plus 5. So the variable x here, right? What I'm going to do first, before I take their product, is try to figure out, when are both of these radicals real numbers, right? For what values of x? When are both the radicals, both these radicals, real numbers? Right. And the answer to that question is just And look at the radicals, and they're both even roots again. If they were odd, or if this was a cube root and a cube root, I wouldn't worry about it. I'd just be like, oh, I can plug in anything, right? Because you can take odd roots of anything, and that's in fact going to be my next example. But they are both even roots. Okay, so the radicands, the x minus 5 and the x plus 5, notice the word and there, they both have to be non-negative. So when are both these radicals real numbers? The answer is when x minus 5, right, this radicand is non-negative, so greater than or equal to 0. Right, that's what it means to be non-negative. And when x plus 5, the other radicand, because it's under an even root, is also non-negative, right? When x plus 5 is greater than or equal to 0. Now look at this. What we have here is one of those compound inequalities, right? This with the word and connecting. And I put out a video, a little while back before this about solving compound inequalities involving the word and. So remember, you solve each one separately and then find the intersection of the solution sets. So let's do that. Here I'd be just adding 5 to both sides. So when x is greater than or equal to 5, and at the same time, and then this one I'd be subtracting 5 from both sides. X is greater than or equal to negative 5. And let me show you a little picture of a number line where we look at these, and we're going to find their intersection. All right. So here's a real number line. Say the 0, separate the positives from the negatives. And all the numbers greater than or equal to 5, I'd say 5 would be the right of 0. There's 5. All the numbers greater than or equal to 5 are over here. Right? 5 is included. Right? 5 is equal to 5, so I put a little solid dot over it. And all the numbers greater than 5 are 6, 7, 8, 9, all those numbers there. Then all the numbers greater than or equal to negative 5, here's negative 5 over on this side of 0. All the numbers, equal to negative 5 is negative 5 itself. And then all the numbers greater than negative 5 are again to the right, negative 4, negative 3, negative 2, and so on. And again, the word and is in this. Right? I need both of these to be true in order for both the radicals to be real numbers. Look at where the overlap is. All right, we're looking for the intersection. And that's all these numbers over here. All right, all the numbers 5 and greater are in both of these solution sets. All right, this is the intersection of these two. Well, the intersection is simply, again, the numbers 5 or greater when x is greater than or equal to 5. So right here, this gives me what's called the domain of this expression. What's allowed to be plugged in to this expression. Okay, so the domain of this expression is just simply values of x that are greater than or equal to positive 5. All right, now this isn't the answer or anything, but it's just telling me what's allowed to be plugged into these values of x and make both these radicals real. Right? Yeah, because think about it. Try it out. Plug in a number 5 or greater, like 6. 6 minus 5 is positive 1. 6 plus 5 is a positive 11. And they're both real. But if you plug in a number less than 5, right, that's not in this, like say 4, you see how the first one will be a non-real number. If I plugged in 4 for x, you'd have the square root of 4 minus 5, which is the square root of negative 1, the square root of a negative. That is not real. All right, so only the numbers 5 or greater, I'm seeing down here in my picture, only the numbers 5 or greater are allowed to be plugged in and actually give me real numbers for these radicals. Okay, so continuing on, now that I know the answer to that question, now that I know when these radicals will both be real, that'll tell me when I can use this property. All right. So when the value of x is greater than or equal to 5, we can do that product. We can use that product property. The square root of x minus 5 times the square root of x plus 5 will be equal to the square root of, and then the product of these two, right? And again, put in, usually when there's a product and and a factor has multiple terms, like x minus 5 has 2 terms and x plus 5 has 2 terms, I'll put parentheses around those factors. So one factor, x minus 5, times, and then the other factor, the other radicand, x plus 5, the quantity x plus 5. And if we simplify this, actually FOIL, right? Distribute the x, distribute the negative 5, or you can think, hey, these are two binomial conjugates, right? The conjugate of x minus 5 is x plus 5. This is the square root of, x minus 5 times x plus 5 is x squared minus 25. And this is it right here. Okay. Now, be careful. I'm going to write up a little statement here that's very important. I see too often, I'll write a little don't down here. Don't do the following. Very often, I'll see people do this. You got this square root of x squared minus 25, and then they decide, oh, well, I'm going to take the square root of x squared, so x, right, because x is greater than or equal to 5 here. So if x is greater than or equal to 5, the square root of x squared, should technically be the absolute value of x, but, x is a value 5 or greater, so it's already non-negative, so I can just call it x. Then minus, and then the square root of 25 is 5, and they'll say, this is x minus 5. That is incorrect, right? This is wrong right here. And it's very easy to check that this is wrong, because all you need to do is plug in some value for x and see that they're not the same. How about if x were, again, just pick a number greater than 5 here. How about if x were 6? If x were 6, the left side you'd have the square root of 36 minus 25. 36 minus 25 is 11. Right, you'd have the square root of 11 on the left. On the right side, you'd have 6 minus 5, which is 1. That is not correct. Right? The square root of 11 is definitely not 1. All right, so the point I'm trying to make here is this. When you see the square root of a sum or a difference, right, so the square root of a plus b or the square root of a minus b, that is not equivalent, that is not equivalent to the square root of a plus or minus the square root of b. You don't just split up the terms. This is all wrong. Everything I put down in this box here, I don't want you to do. All right. So this square root of x squared minus 25 as the radicand there, that's the way it's going to stay. You don't split them up. You don't take the square root of each term separately. The only time you can split stuff up is when you have a product, right? If I was looking at this property here, you see when you have the square root of a product, then you can split up and take the square root of the first factor times the square root of the second factor. And only if these are real, right? Only if these end up being real numbers can you do that. But the square root of a sum, I can't say it enough, the square root of a sum, you cannot split up. You cannot take the square root of each term separately. Okay, so let's check this out. So we're saying, when x is a number greater than or equal to 5, the square root of x minus 5 times the square root of x plus 5 will be equal to the square root of x squared minus 25. Let's test that out with a couple values, right? Well, I'm just going to pick one and just say you can pick whatever you want. How about if I let x be, again, I need x to be a number greater than or equal to 5, so both of these radicals are real. How about 9? All right, I'll just let x be 9. So if I plug in 9 for x, we have the square root of 9 minus 5. I know that that's 4, but I'm going to leave it like that right now. And then times, and then the square root of 9 plus 5. All right, so this is the square root of 4 or 2 times the square root of 14, and we're getting 7.4833147774 and so on, right? Crazy decimal, never ends, never repeats. All right, and let's see if the other side. So I plugged in 9 for x on the left side, these two here. Let's plug in 9 for x in what we said it was equal to, right? If these are truly equal, they should have the same value for any value of x I plug in that's greater than or equal to 5. So square root of 9 squared, right? X squared, and then minus 25, all inside the radical, right? All inside the square root. And look at that, it's the same number, and it should be, right? As we've said, whenever x is a number greater than or equal to 5, this times this should have the same value as this square root of x squared minus 25. Fantastic. Okay, so a lot to pay attention to there, I know. But when you see a product of even roots, you really have to worry about, are my radicands non-negative, right? I want both of these to be real numbers. All right. So my last example, again, is I'm going to ask the same questions I've been asking. Can I use this property? Are these two radicals real numbers? But this one's easier. I have the 7th root of 5 times p times the 7th root of 4 times p cubed. Right, so the radicand of this radical is 5p. Radicand of this radical is 4p cubed. But notice now that these are odd roots. And you can take odd roots of any number. So the radicands can be any number. All right, so the domain for this problem, the domain for this expression, domain, the value I replace p with can be any number. P can be any real number. I don't have to worry about whether or not these are non-negative, because again, these are odd roots that I'm taking. So p can be any real number. Wonderful. All right. Okay. So these are going to be real no matter what. All right. So for any value of p, both of these radicals will be real numbers, and I can use this property. So the 7th root of 5p multiplied by the 7th root of 4p cubed will be equal to the 7th root of 5p times 4p cubed. That's simply just you can rearrange the factors here. 5 times 4, then times p cubed. This is the 7th root of 20, right? The 5 times the 4, and then p times the p cubed would be p to the 4th, right? You add the powers when you multiply things with the same base, and there you go. All right, and we can check that out, test it. All right, this isn't really proving anything, but we're going to test out if I'm saying this product is indeed equal to this, they should have the same value no matter what I plug in for p this time, right? P can be anything. So off to the side on the calculator, I'm just going to, how about let's plug in a negative number this time for p, because you can. How about I plug in -3 for p? Why not? So I'm taking I'll do this expression first, right? So I'm doing the 7th root, right? So I want an index of 7. and then the radicand is 5 times, and then usually you put negatives in parentheses, negative 3. Okay, there's the 7th root of 5p, where I'm letting p be negative 3, and I'll let p be negative 3 in this one as well, times the 7th root of 4 times, and then I'm replacing p with negative 3. So the parentheses negative 3 to the 3rd power. Alright, let's see what crazy number we get here. But it should be real. They're both real, no matter what p is. Alright, so when p is negative 3, this 7th root times that 7th root, this expression has a value of 2.874101788. Again, some crazy decimal. Alright, well, let's see what the value of this expression is, right? What we said this was equal to. Let's take the 7th root of 20 times, and then again I'm replacing p with negative 3 this time, negative 3 to the 4th power, all in the radicand there. And if they truly are equal, they should be representing the same value, right, no matter what I plug in for p. And oh, look at that, 2.874 or so on, right? It's the same number. And try it out with other numbers. Plug in different values of p, and you'll see that this expression has the same value as this expression. It won't always be 2.87. It depends on what value you plug in for p, but they will be the same value every single time. Okay. All right. So again, the key to remember here, the big point made in this video was, if you're going to be using this product property, taking the product of 2 square roots or 2 cube roots or 2 fourth roots, etc., and you want to put them together and make a single root, you can only do that when these two factors, these two radicals, are real numbers, right? This is a property of real numbers only right now. Okay? Alright, I like to say at the end of these videos, try the best you can to learn the material on your own before you go looking for help. I find that people who take the time and effort to learn things on their own tend to remember them for longer and remember the material better. So obviously read the material, read through the author's examples, perhaps even try to work out solutions to some of the author's examples before you see how the author did it, and then compare your work to the author's and see if you can learn from some mistakes there. Obviously, work on loads of exercises, practice problems, look up the solutions to those wherever they're made, if they're ever made available, so you can check your work, keep track of your progress. And of course, don't just give up on a problem or an exercise after one attempt. Very often in mathematics, there are several approaches that'll work for a particular problem. So I mean, if after several approaches at a problem you're still not getting how to do it, perhaps you should read the material again, maybe even a 3rd time, more slowly, more deliberately, take notes. Because if you've been working on some problems too, you probably have a better idea as to what the author is expecting of you, what the author wants from you in that particular section. So then reading through it again, and again maybe even a 3rd time, you'll know better what to look for. Or maybe you'll catch some things that you didn't catch the first time, or things will click in your mind that didn't click the first time through. But if after that, if after several read-throughs of the material and several attempts at problems, you're still not getting it, it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos on the subject. There's tons of those too. Videos like this one, or plenty of other ones out there that are better than this one, better than mine. I assure you they're out there and they're easy to find. But just stay persistent. Keep at it. Don't give up. Keep practicing. And above all, and I think this is the hardest part, is to try to stay positive about the subject. If you're struggling, if you're failing a lot, that's a good thing. The best, you learn the best through failure. You learn the best through struggles. Because once you fail at something, on one attempt, then you know what not to do the next time, and you can hopefully move forward. And I know it's easier said than done. Stay positive about the subject. A lot of people go into something thinking they hate it. They've always hated it. It's going to be boring. That if you think that going in, you're probably going to continue to think that throughout the process, and then think it afterwards, and it's going to make the learning experience that much worse for you. So try to go in with an open mind. Thinking I'm going to read this today, I'm going to practice these problems today, and I'm going to learn something. I'm going to enjoy learning it. I'm going to take something, away from this, from my class, from my life, whatever. Just something good's going to come out of this today. I believe I can do it. I know I can. It's amazing how a change in attitude can, affect the learning experience. So try to, stay persistent, keep practicing, stay positive, and don't give up. And I just know you'll get it. And thank you very much for watching.